We're talking about internal regulation, how your body regulates itself. Right now, I am recording this, and it is 89 degrees outside. 89 degrees, and it is hot. I have a fan on, but I have to turn the fan off because if it's too loud, you will hear it and it will be annoying. So it's very warm in my room right now. The hotter it gets, the more uncomfortable it gets, the less likely I am to be in a good mood. It's going to affect my ability to continue to record this lecture. Temperature is important to functioning. If it were the opposite, if it were below 10 in my room, boy, I would be super cold. So our bodies don't function well if they're not at the correct temperature. Too much or too little is bad for us. That is why our bodies try to attain what is called homeostasis. Homeostasis is our brain's control over our bodily processes to keep things balanced. Think of homeostasis like your brain's thermostat, right? If the temperature gets too hot, your body starts sweating so that you can cool down. If you get too cold, your body will burn energy to warm you up. Look at this cute little bird. Now, usually this bird has two legs, but you can't see one leg. Why? Not because this bird had a tragic car accident, but this bird is holding one of its legs very close to its body in order to warm it up. So some birds will stand on one leg and alternate leg to leg in order to regulate the temperature of their body. Warm one part up while still standing, and then switch to get the other part warmed up. Toucans don't just sell Fruit Loops, they also use their little bills to radiate heat in order to cool down their body. Now, when it gets cold at night, they cover their bills so that they don't lose any more heat. So their bills are a great way of maintaining homeostasis. Oh, look at these cute little rodents. Now, the cutest thing about these cute little rodents is that they have no hair, they have very thin skin, and very little body fat. So, as a result, they are very vulnerable to the cold. So, Mama Rat has to make sure to protect these little guys because if they're exposed to the cold for too long, they could die. Sad little buddies. Come on, get a little space heater, right? And then just radiate some of that heat, warm them up. So, as mentioned, homeostasis is our brain's ability to take into account different information that it receives from the body and balance things accordingly. So, it could be temperatures, level of water. That's why you feel dehydrated, right? Oxygen, glucose levels, calcium, protein, fat, and acidity, and more, right? We have a set point, which is a place that a level that our bodies are trying to maintain. And this is maintained by a negative feedback loop. A negative feedback loop is when if you have more of something, something else brings it down, right? So think of it like the volume control on your computer or on your phone. If the volume gets too loud, then you bring the volume down, right? So if the volume gets too low, you bring the volume up. The negative feedback counteracts for the change. You have that set volume that you want. And so if it's too much, you bring it down. If it's too little, you bring it up. Negative feedback. In case you're wondering what positive feedback is, it's when one change causes an increased change in something else, which causes an increased change in something else, which causes an increased change in something else until it cycles out of control. If you've ever worked around a speaker and a microphone, you might hear what's called feedback, right? And this, what ends up happening is the microphone is too close, that's a microphone, is too close to the speaker. So the speaker makes sound, the microphone picks it up, sends it to the speaker, which makes sound, picks it up, sends it to the speaker, and one small sound becomes amplified multiple times until it becomes this loud screeching sound that everybody hates. So the body isn't working on positive feedback, it's working on negative feedback. Now, in addition to homeostasis, we have what is called allostasis. And allostasis is our brain's ability to predict what we're going to need, right? So if we think that we're about to be in a cold situation, our brains can start preparing for that, right? If we know that we're going to be hot for a very long time, our brains can prepare for that. So instead of just constantly reacting to what's happening in the environment, our brains have the ability to prepare our body for specific external stimuli. So, as mentioned, our body temperature is important when it comes to, staying alive. So, making sure that our temperature is properly regulated is one of our body's priorities, right? In order to maintain our temperature, it requires twice as much energy as all the other things that our body does. So that brings us to what is called the basal metabolism. Basal is the minimum, right? So the minimum metabolism, the energy used in order to keep your body at its consistent temperature while at rest. So when your body's not doing anything, what's the minimum amount, the basal amount of energy needed in order to just keep it alive? If you remember, like maybe your third grade science class, you might remember learning about the difference between warm blooded and cold blooded animals. Instead of saying warm blooded or cold blooded, we're going to refer to cold blooded animals as ectothermic or poikilothermic animals. Uh, Thermic, referring to the fact that we're talking about temperature, poi, referring to the fact that it varies. So, warm blooded animals, referring to the fact that our blood is warm because our metabolism keeps it warm. Cold blooded, ectothermic animals, their temperature is sensitive to the external temperature. So, amphibians, reptiles, and most fish fall into this category. They don't have that same basal metabolism that's keeping them at a consistent temperature. They regulate their temperature by moving to warmer or colder parts of the environment. So if you've ever seen a lizard on a hot rock in the evening or on any rock, maybe you didn't check the temperature of the rock, but if you see them on a rock during the evening, rocks tend to hold temperature for a very long time. So the rock is going to be warmer than the surrounding environment. So that's what they're using to keep their temperature warm. Now, mammals, in all of our superiority, right, we are homeothermic or endothermic. We can use internal mechanisms to control our temperature. Mammals and birds, who would have thought? Birds, you're killing it. This requires energy and it requires fuel. So we need to eat more, right, in order to maintain that basal metabolism. Sweating and panting are things that we do to decrease temperature. So if you've ever seen your dog panting, cats do this too when they're overheated. It is what they do to cool themselves down. Sweating works because when there's moisture anywhere, it's going to cool you down. Now, if you need to increase your temperature, you can shiver. You can decrease blood flow to the skin. You can also just fluff out your fur, as I'm sure all of you have been doing for the past, couple months before it recently warmed up. So that is one way that, or that's what a homeothermic animal or bird will do. By animal, I meant mammal or bird. Here you can see a moose engaging in homeostasis. It's not using internal regulation, but it is seeking the pool for external regulation of its body temperature. This is an option for living organisms. These ducks, you can't tell, they're technically not ducks or eiders, but they gather together to stay warm during these freezing cold Arctic moments. But what ends up happening is not only do they keep warm, but their combined warmth melts a hole in the ice, which allows them to fish while they are huddled together. So they use each other not only to survive in the short term by staying warm, but survive in the long term by creating opportunities to find food. In extreme cold, our poikilothermic friends can do some pretty cool things. So, as you might guess, if the body temperature drops below freezing in any animal, that's going to cause issues. Blood is kind of made out of water. So, if blood freezes, that's going to cause ice crystals to form in the cells and in the blood. Not a good idea. Highly do not recommend, right? Amphibians and reptiles might burrow underground in order to avoid the cold, but some insects and fish can create these antifreeze compounds that allow them to survive in these very cold temperatures. And also, some of them have the ability to repair damage caused by freezing blood or cells. We, and by we I mean mammals, have evolved to have a balanced temperature of around 98 degrees Fahrenheit. Why am I not mentioning the fact that it's 37 degrees Celsius? Because we're in America, baby, and America does America things America way, right? So when we have our muscles that are warm, when we have warm muscles, that prepares us for vigorous activity. If you were wondering why I'm emphasizing warm, well, if you're about to exercise, what do? You warm up, and then your brain explodes, right? You're like, oh, that's what a warm up is, right? Having warmer muscles means that you're more prepared to do vigorous exercise. It means that you're less likely going to injure yourself. So you're obviously thinking, I know you are. This is the question that you were just about to draft this email and send it to me. Why not just have our bodies be as warm as possible? Why not go to 74 degrees Celsius, right? Well, the more heat that we need, that's going to require more energy. You think you eat a lot now, double your body temperature, and you're going to need way more energy to burn all of that food in order to. I said that weird. In order to get all that energy, you're going to need to eat more and burn all of that food in order to get your temperature higher, right? The other issue is your body kind of relies on proteins, and if those proteins are broken down, which can happen at higher temperatures, you're going to lose some of those useful properties of those proteins. And if you happen to be of the male persuasion, you might be aware of the fact that your little spermies are sensitive to temperature. In case you did not know why the testes are contained outside of the body, which if you're ever kicked You you go, why? Why are they contained outside of the body? They're so sensitive. Well, the reason for that is by being outside of the body, it keeps them slightly cooler. And by keeping them slightly cooler, you prevent them from getting damaged by the heat. So a slightly below body temperature container, which is your testicles, the that will ensure that they last longer. So if your body were running 150 degrees, well, you would not be able to reproduce, which for some people, that's a great option. Just to be clear, I do not recommend having a body temperature of 150 degrees Fahrenheit. You will very likely die. So please don't, please don't do that. There are other ways to lower your sperm count. So we often talk about the five senses, but your body actually has more than five senses. One of those senses is temperature. That's why when you like touch a hot surface or a cold surface, you know that it is hot or cold because your body can respond to temperature. Now, your hypothalamus, specifically the preoptic area and the anterior hypothalamus, respond to the your body temperature, right? So it receives input from all the temperature receptors in your body and decides what's going on, right? And then it will send signals to either pant or sweat, panting if you are a dog or cat, sweating if you have skin, uh, or if you are cold, you might start shivering, right? That kind of automatic muscle response, right? That is by creating kinetic energy, you're generating heat. Uh, Also, the preoptic area and the anterior hypothalamus receive input from the immune system. Why? He wonders, knowing the answer. Well, have you ever gotten sick and had a fever? Why does a virus give you a fever? The virus doesn't actually give you a fever. Your body gives you the fever. Your body raises its temperature to make your body uninhabitable for the virus. So to aid your immune system, your body goes, well, our white blood cells are doing some fighting, and that's great. But let's see what else we can do, right? Let's raise our temperature and boil these, jerk faces out of here. So part of the reason we have a fever is because we're receiving this input from our immune system. So we're raising our body temperature to help fight this virus. So we have our hypothalamus over here, and when we make it a little bit larger, we can see the anterior hypothalamus and our preoptic area. So as I mentioned, the immune system sends signals to that area. Two things that are responsible for that are prostaglandins, which are basically lipids, but they act kind of like hormones, and we remember histamines. And these cause shivering, increased metabolism, and fever. But this area isn't the only area involved in temperature regulation, but it is a primary area for controlling sweating and shivering. So here we can just see a little map of how things work, right? We have temperature receptors in the skin, so maybe your hand touches a hot rock that a lizard was just on, and you feel that it's warm. You have the temperature receptors in the brain and your other organs, right? Maybe you have a little infection and you're having an immune response, and your prostaglandins and your histamine are being sent, right? So all that is received and tells the rest of the brain and body to respond. Fever, yeah. So fever is an increased body temperature past the set point, and it is directed by the hypothalamus. The benefits to it is, as I mentioned, if you have a certain infection, it's going to cause bacteria to grow less vigorously. It also accelerates the work that your immune system is doing. Your immune system works hard. It's like hot yoga. And your immune system's like, yeah, I'm going to get that flow going, right? Once your fever gets above 103 degrees Fahrenheit, it's doing the body more harm than good, right? At this point, you're going to see negative side effects. And if you've ever had a very high fever, you know that it's not necessarily fun. Your perception of the world starts to change. It's very disorienting, right? I have a friend who had dengue fever, and he described it as it felt like his brain was boiling. Super fun. Fevers above 109 degrees Fahrenheit, again, I refuse to acknowledge Celsius, are life-threatening. Now let's talk about thirst. Thirst is when you're scrolling through Instagram and you see an attractive person who you followed recently, and oh, nope, that's actually not. Different definition of thirst. So thirst is when your body realizes that you need to hydrate, right? We are 70% water, and we need to replenish the water that leaves our body. It leaves our body when we sweat. It leaves our body when we engage in elimination. So when we poo poo and pee pee, right? We need it in our blood. We need it in all parts of us. Our cells need to stay hydrated. So the uh, uh, the the balance of water in your body determines how the rest of the chemical reactions in your body occur. So dehydration is a very dangerous situation. So right now, if you haven't, had any water today, maybe just have like a little sip, You'll probably feel better. Unless you already had a little sip, then don't have another sip. If you already had a sip, you're good. If you haven't had a sip, drink a little sip. Then come back. I'll be here. Remember your kidneys. You probably haven't thought about those in a while. Well, they're pretty useful. So, as we mentioned, water is very important for our body. But urination is one of the key ways that we eliminate waste in our body. It's very quick and easy. Uh, I was about to say you don't have to sit down to do it, and then I realized that that's my male privilege talking. So I'm sorry. I acknowledge that I have privilege, and I apologize for not being able to see things from just my perspective. But when you pee, you're getting rid of waste, but you're also getting rid of water. Your kidneys play a very key role in this process because they can make your urine more concentrated so that you're not eliminating as much water, but you're still eliminating waste. So if you are trying to conserve water, you can sweat less, or you can excrete more concentrated urine. Thanks, kidneys. If you uh, Another way of conserving water is just by drinking a lot of water and not getting rid of it. So if you need more water for whatever reason, your body can make you feel thirsty, so you drink water, but not immediately get rid of it. But once you have too much, it will tell you that you need to pee, and you'll go do it. And you will stand or sit or lie down or squat or however way you want to pee. All methods of peeing are normal, and I want you to know that whatever way you choose to pee, I support it. So to regulate the amount of water, our posterior pituitary can release a fun little hormone called vasopressin. It raises our blood pressure and constricts our blood vessels. And if we don't have enough water, it helps compensate for that. So it's anti-diuretic. So what it does is it tells our kidneys to reabsorb water And when we pee, it's going to be highly concentrated, as mentioned before. Again, when we're talking about thirst, we're not talking about that friend of yours who somehow has 3 million Instagram followers. We're talking about the body's desire for water. Now, there are two different types of thirst. We have osmotic thirst, which is a result of eating salty foods, and we have hypovolemic thirst, which is the result of a loss of fluids, usually bleeding or sweating. So, just like everything else in the body when it comes to homeostasis, we have a set point for hydration that is 1.5 molar in mammals. That keeps us nice and happy. So all the little bits of matter inside and outside of a cell, referred to as solutes, create osmotic pressure, which means that balance makes sure that only certain things are flowing in and out, right? Water flows across this semi-permeable membrane, right? Because not everything is going in and out, just certain things. And it goes from areas where there's low solute concentration to areas of high solute concentration. And this movement can only happen if there's a concentration on one side of the membrane. If it's balanced, then it can't flow from highest to lowest because they're balanced. So let's just say this were salt, right? You have all these solutes outside of the cell, and you have water inside of the cell. The fact that there is a greater concentration outside of the cell means that the water is going to leave in order to balance the osmotic pressure, which in a normal case is fine, but in an extreme case would cause dehydration of the cell. And because you're smart and you know that water is important for a cell's survival, you know that severe dehydration could be immensely problematic. This is the cell that allows you to remember what osmotic pressure is, and then come the test time, this little neuron dies because it's dehydrated, and you're you drop down from a 96% to a 94%. So as we just saw, right, salt is going to cause a change in that osmotic pressure, which would then create osmotic thirst. So the cells say, well, we are losing a lot of water. So the brain goes, well, I guess there's only one thing that we can do to quench that thirst. Sprite. This class is sponsored by Sprite or water. You can also drink water. Every so often there are terms that I hate pronouncing. Here's some of my favorites. In order to detect osmotic pressure, it can be detected from the third ventricle in the brain, or the OVLT, the organum vasculosum laminae terminalis, or the SFO, the subfornical organ. These detect osmotic pressure and sodium content of the blood. Receptors in your peripheral nervous system, including in parts of the stomach and digestive tract, also give feedback on osmotic pressure. So from those areas, we get input into two specific areas of the hypothalamus, the supraoptic nucleus and the paraventricle nucleus. They control the rate at which your posterior pituitary releases vasopressin. And that, if you remember, tells your kidney to make much more concentrated urine. So these receptors relay information to your lateral preoptic area, which controls drinking. So here we have our subfornical organ, we have our organum vasculosum of the lamina terminalis, and we have our third ventricle. So when osmotic thirst is triggered, the water that you drink has to be absorbed through the digestive system, right? It doesn't just go anywhere, it goes into your stomach. So that is delivered by the brain or by the blood to the brain. And this process takes about 15 minutes. Now, you can drink a lot of water in 15 minutes. And if it takes that long to get that feedback, you might overdrink. So, to make sure you don't drink too much, your body's monitoring the amount of swallowing that you're doing. And it also measures the distension of your stomach, so how much it's stretching, and also of your intestines. If it's stretching too much, then we know that we've had too much water. So if your body fluids are too low, for example, if you lost a lot of blood, the if you lost a lot of blood, then you just have to call your friend and he'll bring it over. But if you lose a lot of blood, your kidneys will release the enzyme renin, which will form angiotensin 1, and that with other enzymes will form angiotensin 2, right? Similar to vasopressin, angiotensin 2 constricts blood vessels to compensate for the drop in blood pressure, right? So if there's less blood pressure, you shrink those blood vessels to maintain blood pressure. It also stimulates neurons in areas related to the third ventricle, and those neurons will send axons to the hypothalamus, where it's released as a neurotransmitter. So there's a state referred to as hypovolemia. The hypo means below. So if you have a hypodermic needle, it goes below the skin. Volemia referring to the volume or amount, right? So this is referring to a loss of blood. So if you have low blood volume, the kidneys will release renin into the blood. Then that will form angiotensin 1. That will turn to angiotensin 2, and then that constricts the blood vessels and stimulates cells to increase drinking. When you have osmotic thirst, you have a preference for pure water. But if your thirst is hypovolemic, you want slightly salty water, right? Pure water is going to dilute your body fluids and it's going to change the osmotic pressure. So a little bit of salt in the water is going to maintain that balance, right? You don't want to solve one problem and cause another. So when you have sodium specific hunger, sometimes your body needs more salt. So this allows you to restore the balance of levels of chemicals in your body. So too much water is a bad thing. Too much salt is a bad thing. Sometimes you'll crave salty foods to balance things out. Sometimes you'll crave water to balance things out. Sometimes you'll crave salty-ish water to balance things out. And that's why if you're ever thirsty and stranded at sea, you shouldn't drink ocean water because it's too salty. So let's just real quickly compare osmotic and hypovolemic thirst. Osmotic thirst is caused by high solute concentration outside the cells. You want pure water to help balance out that concentration, right? And the receptors are located in the OBLT, the subfornical organ, and the digestive tract. If your thirst is hypovolemic, then it's probably caused by blood loss, right? So you want some water with a little bit of salt in it. Think going to the hospital because you got into an accident and getting a saline IV, right? That means that that little bit of salt is going to help keep that osmotic pressure balanced so you don't create a different issue by putting water back in the body. And those receptors are located in the kidney and the blood vessels. Hunger is going to vary in animals. So predators have very large digestive systems that are adapted to the fact that they eat infrequently, right? You don't always have food available. Lions don't just get to go to Whole Foods and order gazelle whenever they want, right? Bears, they eat constantly. Small birds only eat what they need at the moment because the heavier they are, the harder it's going to be to fly. And chickadees eat enough to increase their body weight about 10% so that they can burn off all that energy to stay alive at night. Just in case you don't have enough nightmares already, here's just a python swallowing a gazelle, right? That snake is not going to need to eat for a while. If you ever had a sibling who stole the like last piece of food that you had your eye on, right? At least your sibling wasn't a python, right? They would just eat everything, and then you'd go, "Oh, Brother Python is coming to CBS this fall." Brother Python. You could tell that the publishers were really having fun putting together this this slide because they said small European bird, but it's called great, right? That's just a funny thing. It's called great, but it's a small bird, right? That's the funniest thing on this slide. So this very small bird, whose name I'm not going to say because I am a child and I will giggle, but this bird is going to have very small meals whenever it does, so that it can flit around during the day and just be lovely and beautiful. Our old friend digestion. So, digestion takes large things and breaks them down into smaller things, and then eventually gets rid of the stuff that we don't need, right? So, it starts in our mouth. Our saliva breaks down carbohydrates, and then once things get into our stomach, our hydrochloric acid and other enzymes digest our proteins. And here's our digestive system. Food goes in here, makes several loop de loops, and then comes out. So then, after the stomach, we go to the intestines. The small intestines help you digest proteins, fats, and carbohydrates. That digested food gets absorbed into the bloodstream. The large intestines will absorb water and minerals out of your food, and it will lubricate everything that is not needed, and that will be passed as feces. In the beginning, we have the intestinal enzyme lactase, which is necessary for metabolizing lactose, the sugar found in milk. But after a while, we lose that ability to create lactase, which means that drinking milk can cause gas and stomach cramps. Part of this might be to encourage weaning, right? You can't drink milk forever. At some point, you have to switch to other forms of food. So if your body has a harder time processing milk, you might try other things. Now, many of us have enough lactase to continue to consume milk and other dairy products for the rest of our lives. Some of us don't, meaning that we are a little intolerant to lactose. Hopefully, when I said that, you went, "Oh." Interestingly enough, nearly all adults in China and the surrounding areas lack the gene that enables them to metabolize lactose, so they can only consume small quantities of dairy products. So here's a nice map that shows the parts of the world, at least one-sided, that can easily drink milk, right? So fewer people over here can drink milk, but here's some milk drinking countries, and here's Western Africa, and here's Western Europe, right? So Russia, about 50-50, the lower parts of Australia, right? So a lot of these Southeastern Asian countries aren't really very milk-friendly populations, at least in the adult population. As you might know, there are some myths involving food. Not everything that you hear about food is true. So, eating sugar doesn't make children super hyperactive. Eating turkey doesn't make you sleepy because it increases your body's supply of tryptophan, right? The adage that fish is brain food is partially true. Eating fish may help improve your memory in slight ways, but also any healthy diet is going to aid in your memory, right? So just eat healthily. So obviously, when it comes to feeling satisfied or satiety, uh, part of it is getting food in your stomach, but also the tasting and chewing of the food is a motivating factor. From as far back as 4500 BC, we have found chewing gum. So if you're ever in a class and a professor tells you to stop chewing gum, say, "This chewing gum is older than you. It's older than America. It's older than the Rome." And then they'll be like, "Wait, when was Rome?" I'm like, "I'm not sure. I think uh, I don't know, but probably older than Rome. I'll double check it. I'll Google it right now." So the food is more than just getting things in your stomach. There's a taste and the chewing involved. There was a study done where, and again, every time I talk about a study, I have to preference the fact that scientists do weird things with animals. So they did a study where an animal would eat, but everything that it ate would leak out of the stomach or esophagus, meaning that it never felt satisfied, even though had been doing the process of eating. The feedback from our esophagus and stomach also help us know that we've eaten enough. So, fun fact about the vagus nerve, also known as cranial nerve 10 or cranial nerve X, uh, it is the only nerve that extends past the head and neck, and it tells us when our stomach is being stretched. So, when those walls are being pushed against and we feel full, it sends information about that to the brain. So, when we feel our stomach being stretched, we feel the need to stop eating. So the duodenum is part of the small intestine, and it is the initial place, it's the earliest part of our small intestine, and it's where a lot of nutrients are absorbed. When it starts to distend, it can produce feelings of satiety, and it's where cholecystokinin, a hormone, is released, and that helps us regulate hunger. So between your stomach and your intestine is a little sphincter muscle, and that sphincter muscle keeps the contents of the stomach in, so your stomach can fill faster. So cholecystokinin helps close that sphincter. It also stimulates the vagus nerve to send a message to your hypothalamus that releases a similar chemical. So let's talk about glucose, insulin, and glucagon. Glucose is one of the main products of digestion. It's a source of energy for the body, and it's the primary fuel source of the brain. Insulin and glucagon regulate the flow of glucose into our cells, and excess glucose will enter the liver and our fat cells. So, insulin is a hormone created by the pancreas and it allows glucose to enter the cell. So, after a meal, your blood glucose levels will fall, insulin levels will drop, and the glucose will enter your cells more slowly. Hunger will increase, and then your pancreas will release glucagon. So here we can see this feedback system, right? Let's say you're feeling hungry, so you decide to eat. Because you're eating, the blood glucose levels increase, and you're also increasing the release of insulin. So that insulin helps glucose enter your cells for storage, and you feel less hungry. Over time, you're going to see those blood glucose levels decline, you're going to see insulin levels decline, and you'll feel hungry again, but also glucagon is going to be released. So when glucose levels fall, glucagon is going to stimulate our liver to convert some of its stored glycogen to glucose. So it's another way of replenishing low supplies of glucose in the blood. Insulin is a good thing, but too much is a bad thing. If they stay consistently high, then what's going to happen is the blood glucose is going to continue moving into the cells. That blood glucose drop is going to increase hunger, even though there are high insulin levels. And so food is going to be continually deposited as fat and glycogen. So this could cause weight gain. In some cases, this is a good thing. So if you are an animal preparing for winter and you need to gain weight so you can survive the winter, a lot of constantly high insulin levels could be a really good thing. So here we just see what we just talked about graphically, right? We start with eating. Blood glucose increases, insulin is high. Insulin helps the glucose enter the cells. Hunger temporarily decreases, but the blood glucose levels decline. Oh, sorry, the blood glucose levels decline, but the insulin levels do not. So hunger comes back, which leads to more eating. This would be a positive feedback loop because it feeds into itself. In type 1 diabetes, insulin levels remain super low, but blood glucose levels are high. So you eat more food than normal, but you're excreting the unused glucose and you lose weight. So here we have the cycle of type 1 diabetes. You eat, blood glucose increases, but insulin is low. The glucose doesn't have the chance to enter the cells, so it leaves in your urine and your feces, but you're still hungry. Blood glucose levels stay high, but the cells are starving. You still feel hungry. You still eat, right? Another terrible positive feedback loop. So our body's fat cells produce a peptide called leptin, which signals our brain to increase or decrease eating. This is how we plan for long-term body needs, right? We monitor our fat supplies in the body, and they tell our brain whether we need to eat more or eat less. If we have low levels of leptin, that's going to increase our hunger, and high levels are going to reduce our eating and increase our physical and immune system activity. Now, sometimes high levels of leptin doesn't necessarily mean that you're going to see a decrease in hunger. Some people have less sensitivity to leptin, so their brain receives it, but isn't really triggered to decrease appetite, right? And that could cause obesity. So that sensitivity can also decline during pregnancy or in preparation for hibernation. Puberty, fun fact, is triggered by a certain level of leptin during adolescence. So it all comes back to the hypothalamus, right? Specifically, the arcuate nucleus. So there are two sets of neurons. Some are sensitive to hunger signals, others are sensitive to satiety signals. So, am I hungry or am I full? So ghrelin is a neurotransmitter released in the brain. It acts on the hypothalamus to increase our appetite, and it triggers stomach contractions. Nicotine also stimulates the satiety neurons in the arcuate nucleus, which is why cigarette smoking decreases your appetite. So those satiety-sensitive cells of the arcuate nucleus are dealing with long-term and short-term satiety, right? So we talked about TCK and how that's related to distension in the intestine and the duodenum. We talked about how our body fat releases leptin, which is related to long-term satiety. And we also talked about how blood glucose stimulates satiety cells in our arcuate nucleus. So the one thing that I want you to see here is hunger. Hunger releases GABA, which is inhibitory, and this inhibition of the hypothalamus is inhibiting the inhibitory messages in the hypothalamus. So that tells us to eat, that it's time to eat. So you're inhibiting the inhibitory actions of the hypothalamus, and that's how we make ourselves hungry. So our output from the arcuate nucleus goes to our paraventricle nucleus, which is a part of the hypothalamus. That part of the hypothalamus inhibits the lateral hypothalamus, which is important for eating. So the axons from the satiety sensitive cells that are responsive to things that tell us that we're full deliver an excitatory message to the paraventricle nucleus, and that causes the release of melanocortins. Melanocortins are important in limiting food intake, right? If we don't have enough melanocortins, it's going to lead to overeating. So any input from the hunger cells of the arcuate nucleus are going to inhibit our paraventricle nucleus, which in turn inhibit our lateral hypothalamus. So we've talked about GABA before, but we also have the inhibitory transmitter neuropeptide Y, NPY, and agouti-related peptide, AGRP. So the neuropeptide Y and agouti-related peptide block the satiety action of the paraventricle nucleus and provoke overeating. So we have another pathway coming from the paraventricle nucleus, and that releases orexin. Those are cells in the lateral hypothalamus, and it increases our persistence in seeking food. So it gives us cravings. It tells us we want food, right? So it's related to incentives and reinforcement in general. And when it comes to eating, right? We feel good when we eat, right? It's a self-reinforcing behavior. You eat, you feel better. Yeah, it not only does the job of solving your hungry, but it's also an enjoyable process. What's that you said? You want more nightmare fuel? Well, here you go. So these are digestive systems in rats. Can you tell what the difference between these two digestive systems are? That is correct. One had their paraventricle nucleus inhibited, meaning they didn't get the signal for satiety, so they kept on eating until their stomach burst. Uh, so next time you're sitting at home with a intact stomach and small intestine that haven't burst from overeating, just think your paraventricle nucleus, the real hero of our digestive system. So our lateral hypothalamus is related to our feeding functions. So it controls insulin secretions and it alters taste responsiveness, right? If you're the right amount of hungry, right, food tastes so good. If you're so full, every bite feels like pain, right? So uh, any stimulation to your lateral hypothalamus is going to increase your drive to eat, but damage to the area causes an aversion to food. Can we just leave rats alone? We are forcing them to overeat. We're looking at cross sections of their brain. Oh boy. Here is our ventromedial hypothalamus, right? Here is the lateral hypothalamus, and right here is our paraventrical hypothalamus. Poor little guy. Uh, Ooh, I'm so mad. Oh boy, you really made me mad. Don't worry, he's got a cool tattoo. And he's like, peace, brother. So poor, poor little guy. I'm so sorry. Rest in peace. But it's okay. He's been, he's smoking, so that nicotine is going to suppress his appetite. It all works out for him. I just got an update on the rat. It did not all work out for him. He was smoking a pack a day, and that led to severe lung cancer. You see, rats are very small, so smoking a human sized pack of cigarettes a day will kill them. So I think this is a lesson to all of us about how short and fragile life is. A moment of silence for Mr. Meowskers. I know you're thinking, why does he have a cat name? Well, the scientists that named him are, once again, not very nice. Scientists, leave rats alone. Okay, so oh, they damaged the lateral hypothalamus in this little guy. His name's Cecil, and poor little Cecil. The first thing that happened was he refused all food and drink, so he basically had to be force fed to be kept alive. But we know that the brain is plastic, so it does recover from damage over time. So he moves from refusing all food and drink to eating small amounts of food and sweetened water, but it doesn't drink plain water at all, and it's still not eating enough to stay alive. Now, uh, upon more recovery, it will drink sugar water and it will eat enough to stay alive, but it's going to be at a lower than normal body weight, so still not full recovery. And it still refuses to drink plain water. And now, the fourth stage, it's mostly recovered, and it will eat enough to stay alive, still at a lower than normal body weight. And it will drink plain water, but only at mealtime to help wash down its food. And under very stressful or slightly stressful conditions, even the rat will return to refusing food and water. Thanks, science. I'm glad we learned about what damage to the lateral hypothalamus looks like. Poor little Cecil. But it turns out that Cecil decided to go to Cabo, and he became a cowboy. So that's him with a little a cowboy hat. I have some sad news about Cecil. He was thrown off of his horse on the ranch, and he fell at an angle and broke his neck, dying instantly. So, a moment of silence for Cecil. Here we see some pathways from a little hypothalamus, so to the prefrontal cortex, where we have food seeking behaviors. This is the part of your brain that allows you to plan where you're going to order from or drive through or walk in, right? Then we have the nucleus accumbens, which controls ingestion and swallowing, our somatosensory cortex. So if you remember the little homunculus of the brain, there's a real nice sized chunk that's responsible for the tongue and the senses that we're getting from there, right? So these are all related to eating in some way, whether it's the actual planning out of getting our food, the actual sensory experience, the parts of our musculature involved with moving food through our digestive tract. All of these work in tandem to allow us to eat and survive. So the axons in the lateral hypothalamus, uh, one, they contain dopamine, and or many of them do. They have several functions. One is affecting the taste sensation and salivation response to taste, right? So as soon as you have that one family member or friend's meal that you love when they cook, right? Oh, right? That taste once it hits your mouth and then the salivation response to it. Then we also have the cortical cells that respond to the taste, smell, and sight of food. So sometimes you just see an image of food, right? You're scrolling through Instagram and you see something that somebody posted, or you're watching a cool musical TikTok video. You see, I'm pandering now. TikTok, that's cool, right? The kids like it. Let's say TikTok. But you see a delicious meal being cooked, and your brain is responding to that, right? It's telling your pituitary gland to secrete insulin, right? Or secrete the hormones that tell your body to secrete insulin and controls other digestive secretions as well. So the medial areas of the hypothalamus, any output from the ventromedial hypothalamus is going to inhibit feeding. Any damage to this nucleus leads to overeating and weight gain. Uh, if you do this in rats, poor little guys. I know a lot of people don't like rats, but come on, we've we're just it's fine. It's fine. I'm not even going to name these rats because I'm sure I'm going to hope that something happens to them and that they live a positive life, but something terrible is going to end up happening. So when the medial areas of the hypothalamus are damaged, they will eat normal sized meals, but they'll eat more frequently, and they'll experience what's called increased stomach motility, where their stomach empties faster than normal. So let's talk about brain damage. So any damage to the preoptic area, that's going to cause issues with temperature regulation. Your lateral preoptic area, osmotic thirst due to damage to the cells and also interruption of the passing ions. Lateral hypothalamus, undereating, weight loss, low insulin levels, under arousal, and under responsiveness. Ventral medial hypothalamus, increased meal frequency, weight gain, and high insulin levels, and the paraventricular nucleus, increased meal size, especially increased carbohydrate intake during your first meal of your active period in the day. So, uh, in case you weren't over being mean to rats, here we have a rat with damage to the ventromedial hypothalamus, and here we have a normal rat. You will notice that the rat with damage is just a little bit larger than the normal rat. You can also see a difference in intake compared to the normal rat, and a very significant difference in body weight. So, When we start talking about eating disorders, the availability of tasty, high calorie foods makes animals and people, because we are animals, obese. And we start to find other rewards less rewarding, right? Sometimes there's nothing better than just like a brownie or cupcake or bag of chips, right? Or two bags of chips. So it's not necessarily psychological distress that causes weight gain, but it's the easy availability of high calorie food. Also, a high fat diet before birth can result in the offspring being born with a larger than average lateral hypothalamus. So, when it comes to genes, thin parents tend to have thin children. Heavier parents are going to have heavier children. People who have a mutated gene for the receptors for melanocortin are going to overeat, because melanocortin is responsible for satiety. So it's going to take more food for you to feel satisfied, right? So there's a very strong biological component related to weight loss or weight gain. There's also what's called Prader-Willi syndrome, which is a genetic condition, and some of the markers are intellectual disability, short or stature, obesity, and high blood levels of ghrelin. And remember, ghrelin is associated with telling your body that it's time to eat. So more ghrelin in the blood is going to be associated with more weight gain. So, weight loss is a popular topic in American culture, and sometimes it's made to seem like it's the easiest thing in the world. All you have to do is stick to a diet, and if you have enough willpower, you can do it. But we have to realize that the willpower comes from the brain, but the brain is also telling you how hungry you are, how not hungry you are, right? So if your body, is going to feel full at 90%, and your diet is telling you to eat 60%, then you're going to feel hungry all of the time. It's very difficult to comply with a diet. It requires a lot of hard work, and it's very trying emotionally, right? Just imagine being hungry all the time. It's not fun. So, obesity is considered a disease in the United States. And dieting by itself isn't considered reliably effective. Part of the reason is because it's very hard to stick with a diet for a long period of time. Eating is one of our most basic actions as living creatures. And so trying to control that consistently without ever giving into the temptation of something that's easily available and delicious is a very hard ask. The In order to have weight gain, that also has to be tied with lifestyle changes, including increased exercise. So not only are you limiting what you're putting into your body, but you're trying to burn off more than you're putting in. So there are some drugs that are effective in weight loss. You have to be careful with these, obviously, because they can have unintended negative consequences on the body, and they should be used under the supervision of a nutritionist and a doctor who specializes in nutritional health, so that you're making sure that your diet is still covering your basic nutritional needs. Also, you can use gastric bypass surgery, which basically just, even though you'll be getting the same amount into your stomach, it's limiting the amount that goes through your digestive system. So it's a roundabout way of limiting food intake. Bulimia nervosa is an eating disorder in which people alternate between extreme dieting or compensatory behavior and binges of overeating. So they eat a lot and they feel the need to compensate for that. So some compensatory behavior is what's called purging, so forced vomiting after eating. And this is associated with increased releases of ghrelin and alterations of several other hormones and transmitters, right? So sometimes you just feel super hungry and then you binge eat, but then you feel terrible about how much you've eaten. So then you compensate either by over exercising or by purging or some other method. And bulimia has a lot of the characteristics of drug addiction. This feeling that you have to engage in this specific behavior, the desire to binge eat can feel like a drug sometimes, and we've talked about this because we know that eating just feels good. It feels great. Part of the reason it feels great is because we need it for survival, right? So we've developed to enjoy eating, but when those pathways are acting up and we overeat consistently, then that we start to have certain issues. Last but not least, we have anorexia nervosa. It is characterized by a refusal to eat enough to maintain a healthy body weight. A lot of people who are suffering from anorexia nervosa have this very exaggerated fear of getting fat. So they could be what most people might consider traditionally skinny, but they might consistently describe themselves as fat and ugly and overweight, even though any doctor would tell them that their BMI is at a healthy level or even that they might be a little underweight. But even so, they have what's called body dysmorphia, where they have this distorted image of themselves. They might engage in excessive exercise to keep themselves thin. And we found that people who have anorexia nervosa have lower dopamine levels, but it's hard to tell if the lower dopamine levels are causing the anorexia or if anorexia is causing these issues in dopamine production. So there's a new hypothesis for treatment, which is adjusting temperature levels. So if you remember from early on, we talked about how our temperature affects our body, right? So playing around with somebody's body temperature can affect their appetite. So there was a European trial that showed that 75% of people who had their temperature altered had a recovery from anorexia nervosa, which is a great point to end on because as we continue learning about the body, we're learning about all these individual functions, all these little parts that do very specific things. And sometimes it feels like, one part of the brain does this one thing, and this other part does this other thing, and the stomach gives some feedback to another part of the brain. But we have to remember that our body and our brain are one big ecosystem. So, one of the challenges of understanding what we are biologically is that everything is so intricate and interconnected. But the beauty of that is sometimes the more we understand about that interconnectedness, things that seem to have no real consistent cure can sometimes be solved in very novel and unexpected ways. So that is all for internal regulation. If you have any questions, feel free to drop a question in the comment section or send me an email. Have a wonderful rest of your day.